Okay, Astro 10 class. I hope everyone is doing well, and we're moving on. So on our last section, we left the solar system. Towards the end, we went to stars. We talked about various different types of stars and some of their characteristics. And now we're moving beyond that, beyond stars. So we live in a galaxy, right? It's called the Milky Way galaxy, and there's billions of stars in this Milky Way galaxy. It's a world unto itself, right? So we have our sun is one star. Then there's billions of stars in this. We live in a very pretty spiral looking thing. We'll get to that in a second, right? It's called the Milky Way galaxy. It's a galaxy. And then there are billions, if not more, galaxies. So we're going to be getting into that. So this is sort of a mapping they did from the inside out. Of course, we live in our galaxy, but they think our galaxy, if you look edge on, it's a disc shaped sort of a thing. Has a central bulge. It's kind of, the main body is sort of a disc, and then you also do have stars and clusters of stars. And then smaller galaxies orbiting our galaxy, in sort of a halo type thing. We'll get into that. Okay, so this is the structure of what they believe our Milky Way galaxy looks like. So for reference, this would be an edge-on look. So it's sort of a disk. Our sun would be located here. We're sort of in the suburbs. We're not in the center of this galaxy, right? Our galaxy is a very pretty looking thing. They mapped it from the inside out. We'll get into that in just a little bit, how you would do that. But it's called a spiral galaxy. If you were to look at it from the top, of course we can't see our galaxy from the top. We're in it, but there's all sorts of examples. I mean, we have all our telescopes and stuff. There's billions of these things out there. There's all kinds of examples of different galaxies that have similar structures to this. And there's different types. Ours just happens to be called a spiral galaxy because it has these spiral arms. There's a central bulge, right? So we want to know the components of our galaxy. This is going to be on the test. So our galaxy, the main portion of it, is approximately 80,000 light years. Remember, a light year is a unit of distance. It's how far light would travel in 1 year, so that it's a distance. The main part of it is thought to be about between 80,000 and 100,000 light years, depending how you measured it. Now there also will be, rogue stars. There's thinner sort of stars out here, so this part may extend. I've read may extend out to as far as 200,000 light years, where there's just sort of thin, very wispy sort of arms out there. And then there's another feature called, which is a dark matter, which would be that surrounds our entire galaxy, which would make it even much bigger. We're going to get into that. But for our purposes, the main block of it is about between 80,000 and 100,000 light years is the distance of our galaxy. So our one particular star, the sun, it's often it's called a spur. It's not a spiral. Most of the spiral arms start right from the central bulge. But then there's also these spurs that aren't quite attached. We live in one of those, right? Here's another one. So this would be sort of a top or a bottom view. If you were to look edge on, it has it's a disc shape. It's kind of flat. But then there is a three-dimensional. There's what they call a halo. And here you would have rogue stars, rogue planets, and then globular clusters. Globular clusters are clusters of stars. So there's clusters of stars. Now these things are orbiting. They're not just floating out there. They are subject to gravity. So they orbit around the center. They sort of, this whole globular cluster, all of these stars orbit sort of as a unit. And they would orbit through, the center and come back out here. It seems kind of dangerous that they would do that. Well, yeah, it is. We're probably safer being way out here where we don't have so much activity. Living right in the center would be a much more dangerous place to live, right? Like in the inner city where there's more crime and stuff. So the components you want to know, here's what I want you to know, and you know what I want you to know for the test. So I want you to know that there's a central bulge, right? Spiral galaxies or most galaxies have a central bulge, even other types which we'll get into in the next topic, next session, probably next week. There's a central bulge, so there's kind of a thick area where there's a bulge. Then it's a disk. Well, why is it a disk? Well, for similar reasons that our solar system is in a disk. Remember, all of our planets orbit the sun in the same disk, right? They're all on the ecliptic. They're all on that same ecliptic. So it's a similar formation region or reasons why this disk shape. So the disk shape is common throughout the universe. We see it over and over again. Not all galaxies are disk shape, but a lot of them are, right? So you have a central bulge, right? You have, it's a disk shape. It's composed of spiral arms. These are spiral arms. You have to know that, right? We're off in the suburbs, right? We're kind of maybe 3/4 of the way out from there. There's a halo. So the halo isn't the main thick part, but there's a lot of rogue stars, perhaps planets, dust, particles, and also these clusters of stars called globular clusters. They're clusters onto themselves. And all this stuff sort of rotates, in this way. Whereas the disk itself, objects rotate through. Now this thing turns, but it's not like we're stuck in this spur. The way it works is we actually move through the spiral arms. We move through the spiral arms. So that's interesting. It takes about 220 million years for us to travel around our galaxy once. So if you divide that into how old our galaxy is, which is probably 13 billion years old or something like that. So we've gone around how many times, right? Do the math. So what happens is that we travel through the spiral arms. The spiral arms. Think of a traffic jam, right? When you're going through traffic, right? We're in California, so we're used to this. You're cruising along, all of a sudden, like, oh no, there's a traffic jam, right? And you're going, oh man. So you're stuck in a traffic jam. Now, when you're in a traffic jam, there's more chance that accidents will happen because it's more crowded. People aren't paying attention. Everyone's looking at the mattress on the side of the road, which is why this traffic jam started in the first place, right? Well, eventually you get out of the traffic jam. Now, is the traffic jam over? No. You look behind you, it's still there. It's weird. So you drove up onto it. You had to slow down. You got through it, and then when you left, it's still back there because these other people are looking at the mattress. Then there may have been accidents, little fender benders. So it kind of this traffic jam is sort of self-perpetuating. So it could stay there for hours and hours. If you're lucky, you've gotten through it, right? But it's still back there. That's what these spiral arms are like. Their density. There's a lot of physics involved. We're not going to get into that. But they're regions of higher density, right? So we go through these things. We're going through, and we've gone around many times, so we have to make it through this one. Then it's kind of a little bit less dense. Then we have to go through this, and it's a little bit. So we go through the spiral arms. Okay, that is important. That's on the test, but it's a misconception to think this whole thing spins around like a pinwheel. It doesn't work that way. If that was true, these arms would kind of wrap up onto themselves. That doesn't happen. These things maintain their shape for long periods of time, unless they, bump into something or get close to another galaxy where the gravity can tear them apart or something like that. So we move, and all the stars move through the spiral arms. So we would go through this one, then through this area, then through this arm. And then we'd come back around. So that's the way we go through. We go through the spiral arms, okay? So know the components, okay? There's a central bulge, there's a disk, there's spiral arms, there's a halo. A halo, it's a less dense area. It's so it's a three-dimensional ball, beach ball, right? Globular clusters. Know the size, 80 to 100,000 light years, the main structure, right? Know those things, okay? That's our Milky Way. We call it the Milky Way because you can see, oh yeah, and if you go outside, right, go to the desert, you can see an area in the sky where there's more dense. So you kind of look off, there's a lot of stars, but then there's kind of a denser area. Then you look off and it's less dense again. What you're doing, we're here, you're looking into the spiral arm. So you can see with your naked eye a basic structure of our galaxy. That is cool. You don't just take my word for it. Go outside, go in the desert, turn off your phone, turn off your headlamp, let your eyes adjust, and see the structure of our galaxy with your own eyes. It's amazing. It's cool, right? Do that. Okay, and then these are just some depictions, right, where they've taken a lot of images and then sort of pieced together what they think our galaxy would look like from far away, right? Okay, and then here is just, right, there's stars that are in the main disk, the galactic plane. It's a galaxy, galactic plane. And then there's also those stars that are in the halo, and they do orbit around the central bulge, right? They would go through here, they would orbit this way. So they're three-dimensional. Does it sound dangerous that they might hit something? Yeah. Now remember, most of the galaxy is empty space. That's something when you look at the stars in the sky, right? We all know now that the distance between the stars is huge, right? Hundreds and thousands and millions or not millions. The galaxies are just millions, but there's hundreds and thousands of light years. So there's a lot of empty space. So these things, most of the time, they can make it through. Now, yeah, will they perturbate? Can accidents happen? Does the gravity affect things? Sure, it does. But we've made it around this way. But I'm saying, we're safer to be way out here where we are, right? So it's safer to be out here. Yeah, the galaxy, space is a dangerous place to live, right? No guarantees, just as we know with this virus going around, right? We live in a dangerous world, so adapt, right? Adapt. Yeah, so there's the galactic plane, and then there's this three-dimensional. Okay, now this is something. This is important. So here you have the radius of our galaxy, right? So the radius, so let me go back a couple. Right, so the radius of a circle, right, is sort of from the center out to here. So that's the radius, right? So let me go back to this. Let me go to here. So the radius. So as you move from the central bulge, and then here is orbital velocity. So it's the speed that stars are going around in the galaxy. It's the speed. The similar way that in our solar system, Mercury is going around the sun very fast, right? Then Venus a little bit slower, us a little bit slower. As you go farther and farther away, it goes slower and slower, right? So you would suspect, and astronomers suspected, that as stars went away from the central bulge, you would go slower and slower, just like Kepler's law. Well, it was a huge surprise when they found that doesn't happen. They're like, whoa, what's going on? As you go farther away from the center, here's speeds. This line is kind of the average. So here's orbital velocities. Well, a lot of these velocities are similar to these velocities, which are very close. They're going too fast. They're going way too fast. They should be flung out of the galaxy. So here's what it would look like if it followed Kepler's laws. As you got closer to the center, the orbital velocity is speed. Just like Mercury goes around real quick, it's close to balanced gravity. It would be really fast. And as you went farther and farther, right? Neptune is really slow, but the galaxies don't work that way. In the galaxies, the stars that are far away from the center are going incredibly fast. Like, oh no, what's going on? So that's, if you may have heard on the news or sci-fi movies, dark matter. That's where this whole thing of dark matter comes. There's some gravity from somewhere else. Now notice that the structure of a galaxy is somewhat different, right? The structure of a galaxy is somewhere different. When you have the sun, most of the mass is at the center. Then there's a lot of empty space and there's just these planets. It is different in a galaxy, whereas, like say we're here, the sun is here, there's a lot of mass in this spiral arm than in this spiral arm. So the structure is different. You don't have, like in our galaxy, most of the mass concentrated at the center. It is more spread out in a galaxy. However, even saying that, that doesn't account for how fast, for instance, how fast we are going around. We're going around so fast, we should be flung out of the galaxy. We're going too fast for all the matter that's between here and here, right? All the matter between us and here, we are still going so fast that we should be flung out, but we're not. And this happens in other galaxies they can see, right? So it's a characteristic in galaxies. So what they think is there's a substance called dark matter. They call it dark because in the dark you can't see. So it's like a dark room. So it's matter that we can't see. And with all this matter way out here, then that explains that, okay, we can go this fast and it's okay because there's other matter out here. However, we can't see that matter. We can't account for it. But we can measure its gravity. All matter makes gravity. Normal matter, right? There's visible matter that we can see, stars, and then there's the matter we can't see, dust and stuff, right? But dark matter is not even dust. We can't detect it at all, other than it has gravity. So that's dark. So what makes gravity? Matter. Doesn't matter if it's a normal matter that we're used to, or this dark matter stuff, right? So that's an interesting phenomenon. So that was, what was her name? Vera, right? Scientist Vera Rubin. It's on the other set of videos, the core videos. They talk about her. She discovered that, right? So that is huge, right? So there's, yeah, nothing's simple. Well, things are simple in space, but then there's also a lot of complexity. So the stars and galaxies, the ones that are farther away from the central bulge, they're going very fast, and this happens in all galaxies. You look at other galaxies, faraway galaxies, we measure the speeds of stars. Remember, we got Doppler shift, remember that? So we can measure these stars, how fast they're going, and they're going too fast, right? So that's just the way it is. Okay, and then here, you know, like how did they map our galaxy, right? How do we know the general shape of our galaxy? Well, you ever see old maps that were taken by people like Captain Cook and Magellan, right? These ancient explorers that just had their wooden ships. You look at their ancient maps and you're going, that looks pretty good, right? All they were doing, they were just on these boats, yet they came back with these maps and all they had was charts and star charts and these sextant type things and instruments, but they came back with kind of maps of the world, and they weren't too bad considering all they were just on these boats going along the shore, right? But they had a lot of knowledge. They were smart. They had a lot of technical expertise. Well, that's kind of, we can map. What we do is we map the blue stars. We can see what they do is they look for blue and white stars. They go, hey, there's a whole bunch. Well, we can measure the distance to these things, right? If you look at the core videos, it tells you how they do that, right? They look for Cepheid variables. So they can measure the distance to these spiral arms, and they know that we have spiral arms. Let's go back. Let's go back to this drawing again. So yeah, so you kind of have these regions where you have a lot of blue and white stars. Then you don't for a while. Then you have more blue and white stars, right? So they're able to, by the distances. Now you're thinking, well, there's a lot of blue and white stars here, but why are they all, remember, this is where the traffic jam is. And remember, blue and white stars, they don't last very long. They're so hot. Like our sun is going to last about 10 billion years altogether. Well, these blue and white stars, they may only last 10 million years with the M, considerably shorter lifetimes. Well, their lives are so short that they don't ever even make it out of the spiral arm. So remember, there's like these things. There's a lot of it's a lot of density. There's accidents that can happen. Well, when you have all this activity, right? Clouds of dust. There's a lot of activity swirling. These are areas where stars are forming. A lot of stars are forming in these in these spiral arms because they're denser regions. So there's a lot of activity, right? You have dust and gas. There's a lot of activity. Things are going through the big nebula. They start swirling. The disks form, right? Solar systems form. Yeah, and then if you're like our sun that lasts a long time, well, you make it out and you keep going around. But if you're, say, a blue star, you only last 10 million years. Well, say you were born, you only go this far and you're dead because you burn so hot, you burn yourself out. So that's what happens. The blue stars and the white stars, they never make it out of the spiral arm. They burn hot and crazy, right? It's like that movie Blade Runner. Those things that Harrison Ford was going after, right? They never slept, but they only lived half their lives because they burnt themselves out, right? So our sun, thankfully, is a much cooler star, so it's going to last 10 billion years. It has about, what, 6 billion years to go or something like that. So it's going to keep going around. But the hot stars, they don't last very long. They burn themselves out, right? So that's where the structure comes from. It's denser here. So it's denser. And in these regions here, it's like, now there's stars there, but we can't see them. They're dim. There's yellow stars. There's red dwarfs and things. They're not as bright, right? So that's how you map it from the inside out. Pretty tricky. Scientists are tricky, right? Okay. Yeah, be like scientists, right? Scientists are tricky. Okay. And here's just some beautiful examples of other galaxies that are out there, right? Go on NASA website, just type in NASA galaxy pictures, and oh my God, it's beautiful. There's so many structures out there, worlds unto themselves, right? We'll never get there. These things are far away. These things are millions of light years away, right? But we can see them with our telescopes, so they send their energy, right? Okay, so this is just a good, this is a diagram of what they think are. Now notice, our central bulge is kind of elongated. They call this a bar. So it's a spiral galaxy, but ours, they believe, is a barred spiral, where you kind of have the central bulge, but there's kind of these two main structures that stick out, and then you will have spiral arms that start right from those bars. So we are in a spiral galaxy, but we're in a barred spiral. B-A-R-E-D, right? Barred spiral, R-R-E-D, barred spiral, right? So that's the kind that we are. That's going to be on the test, right? Test question. Okay, now here's an interesting, this is a really good sort of diagram that shows, so say there's a gas cloud, huge nebula, and like our sun, it's traveling through the galaxy, right? It's going through the spiral arms. So it hits a spiral arm. The spiral arm, remember here it's safe. So here it's between spiral arms, it's not as dense. It's just traveling along big gas cloud, just like a cloud in the sky, right? A cloud in the sky, it doesn't dissipate, it kind of hangs there. But in space you can have clouds too, right? Well, it hits a spiral arm and it bangs into a bunch of stuff, right? It's all dense, it swirls. Well, here these little dots are showing star formation. Star formation will happen in these density waves, right? So star formation will happen. Well, you'll have white and blue stars. They never make it out. They never make it out. But red stars, yellow stars, they can form, right? The whole disk structure, right? The nebula, it form like the pizza dough. It'll form. So all these stars will make it through. They'll make it through. They'll have their own solar systems, right? Other planets, perhaps like ours. They'll make it through, and they'll keep going around. But the blue stars, they never made it. They've lived a good 10 million years or so, and then life's over for them, right? So this just kind of shows that. So the nebula goes through, but also a lot of stars, that's how a lot of stars can form. So these spiral arms maintain themselves the same way a traffic jam can last for hours. There's a lot of activity, so it keeps the spiral arms, right? It's one of the things that happens. Interesting. And here's just some pictures of different galaxies out there. Like I say, there's billions of these things. Go to the NASA website, right? And, okay. So they're showing how galaxies form, right? Now there's two. So this is what we're kind of used to. You would have a huge area where you have stars and gas and a huge conglomerate. And it's spinning, and like the pizza dough, a disk will form. We're used to this. So on a galaxy, It happens similar to on a solar system, just on a huge, humongous scale, right? Our scale is astronomical units. Galaxy is in hundreds of thousands of light years. Huge. So, but it's the same sort of thing where it's spinning like the pizza dough. You have centripetal force here that keeps this part out here, but the top, gravity, it will fall in, right? There's no top or bottom in space. So it falls in and a disk forms. But galaxies are different. So there's evidence that there's more to it than this. There's the top down, there's also the bottom up there. So what happens is because galaxies are so big, yeah, so a galaxy can form from that whole disk thing we just saw in the previous slide, but it can keep growing afterwards. These things are so big that as they're going through space, they will absorb other smaller galaxies and other stars, anything that comes in their way, so they can keep growing. So unlike our solar system that kind of formed and then there it is, for the most part, right? Galaxies can just keep growing and growing. So so there's that initial disk phase where it forms, but then it can keep growing and get way bigger as it bumps into other galaxies and engulfs other smaller galaxies and things like that, okay? So that's another. So there's a bottom up. There's a lot of evidence that this happens as well. We have smaller galaxies that are coming towards our galaxy that we're going to engulf, right? So galaxies there's a little more to it than just solar systems, okay? Now, what happens at the center of our galaxy? If you look towards the constellation of Sagittarius, right? Towards that way, that is the center of our galaxy, towards Sagittarius A star, right? That's towards that constellation. And they're thinking, wow, well that's pretty amazing. And you know, have you ever heard that there's a black hole at the center of our galaxy? Well, there's a lot of evidence for that. You're thinking, well, Felix, I heard you can't see a black hole because even light can't get out. That's true, but remember, a black hole will have a lot of gravity. We'll talk about black holes more in the next section, but black holes, there's just so much stuff that it crushed through a white dwarf, it crushes through a neutron star. There's so much stuff that it just crushes down into this feature, and then it and mathematically it goes down to some point, but it ends up in some form where it's just so incredibly dense. But what's the evidence for it? Well, this is a diagram that shows the center of our galaxy. These little dots, there's much more now. This diagram is actually kind of old. They have a lot more, but it's showing the orbital paths of stars. So they've plotted data. For years they've been measuring these things. So they know that this star, for instance, has this orbital path. They know that this star has this orbital path. They know that this star has this orbital path. This star has this. So there's all these stars that they know are orbiting something hugely massive at the center. So all these stars are going really fast and are orbiting like crazy. You're going, wow, it's orbiting. There must be something amazing there. What's there? We don't see anything. So what the heck is that? Well, it's a black hole. Black holes are so dense that light itself can't get out. We'll talk more about that later. But you have all these stars that they can measure. They know that they're orbiting. They know their trajectories. They've been measuring these things for years. And they're all orbiting something at the center of our galaxy, in the center of the central bulge, and everything's orbiting it, and they got all these stars really close that are flying around it like crazy. It's a black hole! That's the definition of a black hole. You know it's there because of the gravity. These things can't orbit nothing, right? They're orbiting something. Well, they're orbiting the black hole, and we can't see it. So that's evidence for the black hole, okay? Is that going to be on a test? Yeah, you betcha that's a great test question, right? So evidence, that's the evidence for the black, and it's a supermassive black hole, right? It's huge, many millions times the mass of our sun, right? So it's a supermassive black hole at the center of our galaxy, okay? Pretty nifty, isn't that? Okay, and next video will be coming henceforth. Be safe.